Saw them. We have our beautiful, beautiful pictures tonight. Special request by our speaker that you have the core of the globular cluster Omega Centauri. Okay, and all these beautiful red and blue stars, which are actually ultraviolet and infrared as well as visible light. It covers the full spectrum with wide field camera 3. It's beautiful. More details available on the back. And I hope our speaker will actually talk about that a little bit tonight. Who is our speaker? Our speaker is Mia Bovel. She is going to talk to you about the Harvard computers and the classification of stars. Of course, this was work done a century ago, so computers is in quotes, and you'll understand that in a bit. Next month, I've been having trouble getting people to commit to June. Usually July is my problem, okay? But I've had people trouble, so it's still to be announced, but I'm working on it. Trust me, I'm working on it. I'll find somebody's arm to twist for next June, June 6th. July has actually been moved early because we have Amber Strawn from Goddard Space Flight Center here, and she will be talking on dark energy and new worlds, the science that we hope to accomplish with NASA's W-FIRST mission that will hopefully launch sometime next decade. There will be no lecture in July because we're taking Amber's lecture and counting that as our July lecture. In August, I have a really cool talk for you. The View for Mission Operations, that's not the title. I just made that up this afternoon. She hasn't given me a title, but Courtney McManus, who has worked on mission operations for the International Space Station, and we have the missions operations here for JWST here in the building. She'll be telling you all sorts of cool stuff from a mission operations standpoint, August 1st, 2017. Can't remember all that? You can go to our website on Hubble site. And by the way, Hubble site has been, design has been changing. I don't know how many of you go to our Hubble site website, but we've been changing it and modernizing it. All the content is still there, okay? You can still find us. Finding this page is probably the easiest. If you go to your favorite search engine, type in Hubble Public Talks, you'll find this web page. On the web page, we have our links to our live webcasting, links to the archive all the way back to 2005 in the STSCI webcasting archives, as well as a way to sign up for our email list to get our couple reminders a month about the talks that are coming. The announcements, again, sign up at the website, but if you want to do it the hard way, you can go to maillist.stsci.edu. The mail list is called Public Lecture Announce. If you would like to ask us questions, send us comments, you can send email to publiclecture@stsci.edu. For those of you who like social media, Hubble has several ways of communicating: Facebook, Twitter feeds, Google+, and Pinterest out there for those of you who use those social media. Myself, I have a blog on Hubble site. I have Facebook, Google+, and Twitter that I occasionally do. But unlike the president, I have better things to do with my time. So I have a tendency to do my science rather than spend too much time on Twitter. Okay. Observatory tonight. Yes, the weather is permitting. I talked with Irini, and she should be here about 9 o'clock or so to take a group across the street to look through the telescope across the street. So at the end of the lecture, if I forget, somebody remind me. You'll meet down here with Irini, and she'll take you across the street. All right? And now, okay, my section. News from the universe for May 2017. Our first story tonight, by Jupiter. It's quite a beautiful planet. Thomas, can we take the lights down a bit? There's a little a bit of spillage onto the screen here. Okay, that's good. Thank you. All right. So once a year, Jupiter gets into what's called opposition, okay, where the Sun and Jupiter are on the opposite sides of Earth. Well, this is the point in Jupiter's orbit when it is closest to Earth, because you can see that if it were located anywhere else around its circle, around its orbital circle, it would be further from Earth. So the best viewing, its closest point, is at opposition. Also, it's its best viewing because it's up exactly opposite the sun, so it's not up at sunset, not up at sunrise, where you have interference of that, and you can see it. Now, Hubble doesn't have to worry about that too much, because Hubble's up in space, and it doesn't have to worry about, daytime versus nighttime, because, it doesn't have the atmosphere to look through. However, we often take pictures of the planets when they are at opposition. And you might think to yourself, well, we've had missions that go to the planets. What can Hubble offer? And I sometimes look at these press releases we do and go, okay, but you know what? Oops. Well, let me replug. You know what? This is an observation we have yet to take. Let me try this again. There we go. Okay, there we go. Now we got it. We're back. Great. But you know what? Sometimes we just get it right. So this is our picture of Jupiter at opposition from this year. Isn't that cool? I mean, I remember when we had to have the Voyager missions to go across interplanetary space to get something that looked this gorgeous. And I just love all of the hydrodynamic effects, okay? I'm a sucker for all the hydrodynamic effects of the vortices and the swirls in Jupiter's atmosphere. Plus, you'll notice we've got not only the great red spot, but also we have what we colloquially call red spot junior, officially called oval BA. I much prefer red spot junior. And oval BA formed in the year 2000, okay? We had never seen a second red spot until it actually, well, it formed as a white spot and then turned red a few years later. But it has now been around for almost 15, 20 years. Okay, so we're seeing a second red spot on Jupiter, and it appears to be long-lived. But I just thought this was a really wonderful and beautiful image of Jupiter. Our second story tonight is also from the solar system, Europa's Old Faithful. All right, so first of all, let's make sure everyone remembers what Old Faithful is. Old Faithful is the geyser in Yellowstone National Park that erupts approximately every 90 minutes. Is that right? Is that about 90 minutes, or is it longer than that? Yes. Karen's saying yes, which is actually, incidentally, about the same time it takes Hubble to orbit around Earth. So every time Hubble passes over, Old Faithful erupts, right? Not quite. And so this is a geyser from hot springs, okay? And so the idea is that the water spews up 100 feet in the air or so, right? Well, if you remember, if you were here last year, I told you about seeing a plume on Europa that spews out a little bit further than 100 feet. All right, so you got to understand this image, okay? First of all, the plume is in white, which is really pulled out of the data. It's really hard to see this. It's actually seen in shadow against the surface of Jupiter. So Europa is passing in front of Jupiter, and we're seeing that plume in shadow. It's been reversed here so that you can see it as white. And then the picture of Europa here is not from Hubble. This is actually from the Galileo mission. All right, as remember I said, we get missions that have been there, they got better pictures. So to give you an idea of what we're seeing, we've taken the Hubble data, stretched it in contrast so you can see the plume because it's really tiny there, and then thrown the Galileo image on top of it, okay? This is what I told you about last year. Well, we looked again to try and see if this was a recurring event, and yes, it is. We are seeing another plume. Now, we don't see it every time we look for it, okay? We have done this observation multiple times. Sometimes we see it, sometimes we don't, which gave me the sort of instance of Old Faithful, that it sometimes erupts and sometimes doesn't. What does this mean? Well, the surface of Europa, if you look at it in detail, resembles cracked ice rafts in the Arctic. This is actually the surface of Europa. And you can see all the ices and all the cracks in it, okay? All right, and because we're able to time when it when we saw this plume and where it was on the moon, we were able to narrow down to where we thought the plume was coming from, to these cracks here on Europa. All right? And the idea was to say, all right, why would these cracks be emitting water vapor? Well, turns out that a temperature measure of the surface of Europa shows that that area is 3 degrees warmer than the rest. Now, you have to recognize 3 degrees warmer is going from 92 Kelvin to 95 Kelvin. And this is an absolute scale. So this is minus a couple hundred degrees Fahrenheit, okay? So when I say warmer, I really should be saying 3 degrees less totally, absolutely frigid, okay? But it is actually warmer. So the idea behind all this, all right? The idea behind our understanding of Europa is we have understood that underneath its icy surface, there is probably a liquid water layer. Now, originally, we thought that that icy crust was about 100 kilometers thick. And if you wanted to sample the water, you'd have to drill down through 100 kilometers, which is not a very easy task. However, if we're seeing these plumes, and we're seeing them more than once, it may indicate that there are pockets of water, maybe not the ocean underneath a layer, but maybe there are pockets of water that are just a few kilometers down in the ice. If you remember what we learned about Pluto last year, cryotectonics is really much more important in the outer solar system than we'd really understood. So we learned that also about Europa, that the ices move and crack, and the dynamics of ices is a lot more than we had previously suspected. And perhaps there are pockets of water that are 1, 2, few kilometers down, then that raises the prospect for being able to go there, drill down to it, or melt down to it, and be able to sample it. Now, why would we care about water? Well, because there are 3 things required for life in the universe as we know it. 1 is carbon. Carbon's everywhere. 2 is a source of heat. We got sources of energy all over the place. And 3 is water. So our search for life in the universe is often just boiled down to a search for water. Wherever liquid water can exist, perhaps life can exist. And we have seen life in all sorts of extreme places here on Earth. So Europa is one of our strongest candidates for possibly having life elsewhere in the solar system. And the observations from Hubble have done yet another small part in convincing us that, hey, this is a really cool system. We ought to continue to investigate it. And yes, it's become one of our main points of study for trying to look for life in our solar system. All right, third story tonight, our 27th anniversary perspectives on spiral galaxies. The 27th anniversary is of this event, the launch and deployment of the Hubble Space Telescope. It has been 27 years. Isn't that great? All right, we've been up there for 27 years doing science. And so every year they ask us to do a really cool image for the anniversary. And it's, I gotta say, one of the gentlemen who helps choose these images is in the audience right now, and he can confirm that it's really, really hard to keep outdoing themselves every year. So this year we chose some spiral galaxies, okay? And these spiral galaxies are in the Virgo cluster. So we're gonna zoom in from a wide field view. I'm gonna keep going down and zooming in until we come into these 2 spiral galaxies, NGC 4302 and NGC 4298. Such wonderful names. And those are the 2 spiral galaxies we chose for the Hubble 27th anniversary image. Now, if you notice at the end of that movie, it zoomed in visible light and then switched to infrared. So let me show you those in detail. Here is the Hubble image using visible light, all right, and this is the infrared view, all right, using the near-infrared capabilities of Hubble. So visible light, infrared light, and you can see that the difference in how we view the galaxies changes according to the wavelength in which we view them. Well, we also wanted to give you another perspective on them. So we created this visualization to help you understand the shape of these spiral galaxies. And so by rotating those galaxies in 3D, by the way, those are just computer models of the galaxies. We don't know the exact details. Matter of fact, the galaxy on the left, NGC 4302, the model that we used is a model based on the galaxy M51, the Whirlpool galaxy. Because we're seeing that galaxy edge on, we really can't tell the true three-dimensional structure, so we had to use, as I like to say, a stunt double galaxy for it. But that gives you a mental model of what you're seeing in this image. And when I show you another image, which is also in the Virgo cluster, I show you this image of all these various spiral galaxies. You now have the mental model in your head to interpret this and say, okay, these are all pretty much those same disc-shaped galaxies, but seen at different angles. So in doing this, you gain a mental model of how spiral galaxies look, and you can see them in perspective. You can translate images such as this. All right. And now it's time for our featured speaker, Mia Bovel. Mia has been here at the Space Telescope Science Institute for only a year and a half. She gave a wonderful talk last year, and I'm really looking forward to her talk this year. She got her bachelor's and her master's, bachelor's and her PhD from the University of Maryland in physics. She spent a year at the University of Texas at Austin before spending 3 years down in Chile at some unpronounceable institute in Santiago. She said she'd pronounce it for you. She wouldn't make me try to pronounce it. She came here and she does her research on dwarf galaxies, as she likes to say, the smallest of the small galaxies. Generally those in the nearby universe or those in the very distant universe. She doesn't care about the 10 or 11 billion light years in between. She also would like to note that for tonight, she's doing a talk on the women from Harvard, and when she was an undergraduate, she did a research experience for undergraduates at Harvard, working on, of all things, star formation. So, ladies and gentlemen, our speaker tonight, Mia Bovel.
Can you hear me? Okay. And it's Instituto de Astrofísica Pontificia Universidad Católica de Chile. I wasn't going to make him do that again. When astronomers talk about the Harvard computers, we actually don't put quotes around them. This is an image of the Harvard computers. It is a group of women. It is a group of women that worked at the Harvard Observatory over the course of about 40 years. They generally stayed for 10, 20, 30 years, and up until the 1920s, this was the only place where you could be a woman and a professional astronomer, other than some of the women's colleges like Vassar, which has had Mariah Mitchell. But what did they do that was so incredible? And before I get into that, the scientific parts of this story and their contributions to astronomy are so fundamental that you learn about them in your very, very first year. In fact, you learn about them in Introduction to Astronomy for Poets. But the human side of this story, and many of the quotes that pretty much all the quotes that I'm going to be using, come from this wonderful book that just came out called The Glass Universe. This is the same author that wrote Galileo's Daughter and Longitude, and if you're interested in hearing more about this story, as well as many of the players that I'm not going to have time to talk about tonight, I highly, highly recommend that you read it. So if any of you cannot see this from Baltimore. If any of you have ever had the wonderful opportunity of being in an extremely dark sky, you have this lovely view of the disk of the Milky Way galaxy. And when you take that into 3 dimensions, I'm afraid that my visualization is not as good as the one you just saw. I went for the cartoon version. You have, this is that thin disk that you saw in the animation. In the center of most spirals is a bulge surrounded by a halo of stars. I can tell you that in this disk are open clusters, these blue objects here. These are regions that are either still forming or more very, very recently formed stars. In the outskirts of the galaxy are globular clusters. These are old systems. They're 10, 12 billion years old, so roughly approaching the time that I'm interested in. But how do we know this? We can observe clusters like the Pleiades, which I'm sure if you ask very nicely and it's up, they'll be willing to show you tonight. You can see this by eye. The 7 brightest stars are visible by eye in the constellation of Taurus, even from Baltimore. This is an open cluster that is about 25 million years old. And you can see some of the gas here that's still surrounding the stars. So this is very, very recently formed stars. This is Omega Centauri. This is zoomed out quite a bit from the Hubble image that was handed out. This is a globular cluster. It's one of the younger globular clusters. Some of them are billions of years older than Omega Centauri. And so here is a question. How do you find out the age of a star? You can't ask it. It would not only be rude, but I don't think you would get an answer. And the answer to that is you use one of the most powerful diagrams in astronomy, which are color magnitude diagrams, or HR diagrams. This is the Hubble image that you all have. There's a reason that I asked for it. And this is an animation. We're going to take the stars of Omega Centauri, and we're going to zoom in a little bit. This is the very core of the cluster, so it is an incredibly dense star field. Those stars are then going to be sorted. The bluest and hottest stars are going to move to the left, and the coolest and reddest stars are going to move to the right. You're now going to sort them by absolute brightness or luminosity. The brightest stars to the top, the faintest to the bottom. This is the HR diagram. It is one of the most powerful plots in astronomy. In fact, I would tell my astronomy for poet students, you understand this, you're going to pass the stellar evolution section of the class. I called it their cheat sheet. Along here is the main sequence. Our sun would sit about here if it was an omega sun. All the stars, and it's now, I have a better one coming up. Did you notice that it turned off? The main sequence didn't continue all the way up, it turned off. That is how you determine age. This is a more cartoon version for explanatory purposes. Here you have the main sequence. All the stars here are burning hydrogen in their core. And the more massive you are, the hotter you are. You can think of these guys as Hummers and these guys as Priuses. These are going to be brighter, they are hotter, and they also burn out a lot faster. So if the main sequence turns off here, your cluster is about 10 million years old. If when you plot up your main sequence, it turns off here, it's 1 billion years old. Once a star turns off the main sequence, it moves up through the giants or into the supergiants and eventually evolves down. Our sun will become a white dwarf. Objects that are a little more massive kind of hang out here for a bit. They can't quite decide where they're going to sit, and then they blow up in supernova. This is on the y-axis. The vertical axis, we have luminosity or absolute brightness. You're going to hear me use those two terms interchangeably. They mean the same thing. And what this entire talk is about is this x-axis. It's in color from red to blue. It's also in something we call the spectral sequence. And we also, temperature increases to the left. And the fact that I am able to tell you that is because of the Harvard computers. So we need to go back a little bit before 1880. This is the refractor at Harvard. These are not reflectors. Modern telescopes are reflectors. You have a mirror at the base of the telescope. The telescopes that were used to produce these observations are refractors. They have a lens at the top of the long tube. They're much larger for the same size telescope. It's why we stopped using them. At the time, in the 1870s and 1880s, there was this newfangled thing called photography. I don't know if any of you have ever done this. For the younger people in the room, there was a time when you took a picture with a camera and it was on film and you had to get it developed. You didn't just take it with your phone and put it on Facebook or Twitter or Snapchat or whatever the hell the newest thing is. They took images, not on film, but on photographic plates. This is a digitalization of part of the Palomar Sky Survey. This is an actual physical glass plate. Some of these could be about that big. So they were heavy, they broke, and just not the best option. But this was all we had until about 30 years ago. And each of these points is a star. In general, the bigger the star, the bigger the black here. This is a brighter star than that. So you can tell the magnitude of the star, and if you take this image in red and green and blue filters, you can also tell the color of the star, which is how the HR diagram was originally plotted. But we want more information. Welcome to astronomy. This is Henry Draper and his wife Anna Draper. He was a medical doctor who had an astronomy habit. She had the money. And he developed a method for taking that spectra, for taking this plate, and he stuck a prism in front of it. So actually, this is the best graphic I could find on the internet for this. I'm not actually kidding. You have your light from a distant star. You pass that light through a prism, and it breaks it into its components. And when you break that light into the components, you get a lot more information than just the color of the star. This is the spectrum of the sun. So you look at the sun, you see a yellow star. We call it a G-type star. All of these black lines are absorption lines. And each element has a unique set of absorption lines. Think of them as fingerprints. You can identify a human with their fingerprints. You can identify an element or a molecule by its spectrum. The simplest of these is hydrogen. So up here is wavelength in angstroms. Just a second, 1/10 to the, so each of these numbers multiplied by 10 to the 10, so 10 additional zeros will get you meters. So this is 1 in 10 to the 10 meters. Very, very tiny scales. H alpha, H beta, H gamma, and H delta. H alpha is actually one of the most important lines in astrophysics. The more complicated the element, as you move up the periodic table, the more complicated its spectra. Now, the plates Draper took didn't look like that. This is one of the Draper plates. At the location of each star, you see a spectra. In the initial set of plates, each of these was 1 inch across. So if you hold your fingers at about 1 inch, that's how wide each of these things was on the glass breakable plate. Unfortunately, reasonably quickly after discovering this method, Henry Draper died. As was typical of, I think, the entire 19th century, he caught a chill and had a dinner party and went to bed and never got up. And Anna Draper was so devastated by her husband's death that she wanted a memorial to him. So she talked to Edward Pickering. and endowed the Harvard Observatory with money to finish her husband's work and build a Henry Draper catalog of the stars. Because remember, she had the money. And Edward Pickering did something that at the time even Anna Draper wasn't expecting. He felt that women would be well suited to the repetitive and drudgery of looking through thousands and thousands of glass plates with spectra that are an inch wide. Now, years later, of course, you tend to sugarcoat this, and he talks about the criticism is often made by the opponents of higher education of women, that while they are capable of following others as far as men can, they originate almost nothing, so that human knowledge is not advanced by their work. Keep in mind, this is 1880. This reproach would be well answered if we could point to a long series of such observations as are detailed below, made by women observers. This is one of the first times in history that women are making contributions, and Pickering acknowledged the Harvard computers in their work. The first of the Harvard computers was Wilhelmina Fleming. She was a Scottish immigrant who moved to the United States, got pregnant, and her husband promptly left her. So she got a job as the maid at the observatory residence at Harvard. And Pickering knew her. He was the director of the Harvard Observatory at that point. He recognized that she was a little too intelligent to be a maid. She didn't have a college degree, but she was educated. And he hired her as a Harvard computer in 1879. I'd like to point out the other reason to use women: they're paid less. I didn't know if you've heard about that. She promptly leaves a year later to give birth to her son in Scotland, and then leaves him with her mother and her aunt and returns to Boston without him in 1881. I think he eventually makes it to the United States, but it's like 10 years later. And her task was to classify these spectra. So if you remember, this is what she's looking at through a magnifying glass. And she noticed that here is good old hydrogen alpha. She noticed that some stars had stronger hydrogen lines than others, and so she classified them by the strength of their hydrogen lines. The strongest hydrogen line she called A stars. The next B, C, D, you can see where I'm going, all the way down the alphabet. And you'll note that this is not in alphabetical order. And we're going to get to that in a bit. She also discovered variable stars. She found one of the first nova, because they're looking at a set of plates that no one's ever had before. And in general, in astronomy, when you have a technological advance and insane amounts of telescope time, discoveries happen. But later in her career, and for the last about 10 to 15 years that she was at the observatory, her primary duty was to curate these glass plates. These are irreplaceable. You don't have digitalization. You don't have a phone you can take out and take a picture in case you mess up. If something happens to these glass plates, the information is lost forever. She was also responsible with editing and preparing the Henry Draper Memorial Catalog for publication. There are 90 volumes of this. So she also was the effective head of the Harvard computers, their leader, as you will. But unfortunately, I love astronomy. Everyone loves astronomy. I need to pay rent. And this is a wonderful quote. Pickering seems to think that no work is too much or too hard for me, no matter what the responsibility or how long the hours. But let me raise the question of salary, and I am immediately told that I receive an excellent salary as women's salaries go. Because, of course, if you're a woman, your husband's actually making the money. And in general, the Harvard computers were unable to live completely independently. Many of them lived in boarding houses or rented out rooms in their own homes to make ends meet. Because remember, they could be paid less than a man or cheap. Antonia Mari was actually the first Harvard computer. She was related to Draper, and she was the first Harvard computer to actually have an astronomy degree. And that degree was from Vassar, which is where Mariah Mitchell worked. And remember what I said about technological advancement? Well, instead of having those spectra be an inch wide, the plates that Mari got to work on, they were 4 inches wide. And they were far, far more detailed. And you would think detail is good. Detail is generally good, but complicated. And she noticed that in addition to the lines having different strengths, so having different depths, some of them also had different widths. 2 stars that seemed to have the same strength of hydrogen line would have different widths of hydrogen lines. And she worked to try to incorporate this into a new classification scheme. So she threw out what Wilhelmina Fleming had done with the alphabet and came up with a numbered scheme. And this worked, but it was actually a little ahead of her time. And so now we get to the 3 main players in this little drama. They're on my shirt, if you need reference. Henrietta Swan Leavitt and Annie Jump Cannon arrived at the same time as unpaid interns for a year. Both of them then left and were only able to return when another one of the computers got married. She had a degree from Radcliffe, which no longer exists because Harvard now lets women in. And she was also deaf. Not her entire life, but in adulthood. And she was given the task of monitoring variable stars. So you can imagine you've got all these photographic plates, and you're going to see certain stars vary a little bit in brightness. So you're literally looking at this plate, and then this image from 2 days later, and 2 days after that. And she came up with a novel method that allowed her to look at one plate on top of the other, using a negative image of one and putting the positive image of the other on top of it. And down the line, she was looking at a set of variables in the LMC. Here's a very pretty image. It did not look like that on the plates. And she found a class of variables that were already known called Cepheids. And the characteristic of a Cepheid is it rises very, very quickly in brightness, and then falls off slowly, and then rises quickly again, and falls off slowly. And because all of these Cepheids were in the Large Magellanic Cloud, she knew that they were at about the same distance from Earth. And so if one of those Cepheids appeared to be brighter than another, it actually was brighter than another. And she plotted this. As you do in astronomy, you plot things. And she found that the longer the period of the Cepheid, the brighter the Cepheid actually was. And you can see this here, the brighter Cepheid with its longer period, and the fainter Cepheid with the shorter period. This was immediately recognized for what it was. This is called a standard candle. This means you can look at a Cepheid, you can measure its period, and you know how bright it is. And if you know how bright it actually is, and you know how bright it appears to be, you know how far away it is. This was used within a year of her discovery to find that the LMC and the SMC were just a bit further away than they thought they were. And in actuality, they're even further than that. This is her and Henrietta Leavitt and Annie Jump Cannon. Sometime in the teens in front of the Harvard Observatory. They came in together as interns. Annie Jump Cannon arrived because literally somebody got married, so she was hired. She graduated valedictorian of Wellesley in a degree in physics and astronomy. After a brief stint at Harvard, she lived with her parents for 10 years. During that time, she contracted scarlet fever and lost most of her hearing. After 10 years, someone got married. She was able to come on as a Harvard computer. To give you a comparison, a student of her caliber, or Henrietta Leavitt's caliber, or Antonio Mari's caliber today would be off to one of the best grad programs in the world. They would not be living with their parents for 10 years hoping that a position opened up. This is her at her graduation from Wellesley looking through a very, very small refractor. And what she did was reorganize what Wilhelmina Fleming did, accounting for what Mari had noticed in the spectra. Mari had noticed that certain stars, like O stars, had extremely strong helium lines, which other stars, like M stars, with very faint hydrogen lines, did not. And so Annie Jumpcannon did a little bit of reorganization and some editing. She moved the O stars to the top of the sequence, because if you're producing helium lines, then you're hot. She moved the B stars next to the O, and then edited the rest of the sequence down. This is the sequence we still use to this day. It's a little difficult to remember, so we use OB, a fine guy, kiss me, or OB, a fine girl, kiss me, depending on your preference. And so now this x-axis, in addition to being color from red to blue, is now the spectral sequence of O, B, A, F, G, K, M. And by the way, if you ever see this on a license plate, astronomer. In addition, Annie Jumpcannon was the first of the Harvard computers to actually be allowed to shockingly observe. These telescopes are extremely big. This is her in Peru, at the outpost in Peru. They hadn't discovered Chile yet, I don't think. And maneuvering the bottom of the giant refractor there. These telescopes are extremely long, extremely heavy, and nothing's motorized. Today, you sit in a control room. You tell you tell your telescope operator, I want to go point at that, and then the telescope operator punches some stuff into your computer, and the telescope magically moves. There's no magic at this point. You had to physically move the telescope, and this work was deemed to be too physically demanding for the poor, weak, defenseless women. I don't know where they got that idea. So she was the first of them, but not the last, to actually make observations. And she became the world expert in this. And in the summer of 1912, she went to Europe and attended conferences and spoke. And in a meeting that was the precursor to the modern International Astronomical Union, she was very surprised to find that she was put in the committee of the classification of stellar spectra. And I'm thinking she's being a little sarcastic here. And she talks about sitting at a long table and being the only woman in the room. And since I have done almost all the world's work in this one branch, she was the classification of stellar spectra at this point, it was necessary for me to do most of the talking. I wish I could tell you that this has changed. It's better. It is better. I am usually not the only woman in the room. There's usually two others, maybe. But I have definitely been in meetings where this was the case. In 1919, about 7 years after that, Edward Pickering died. His replacement at the Harvard Observatory was a man named Harlow Shapley, who is better known in astronomy history circles as being completely wrong about the scale of the Milky Way galaxy. In fact, he was the one that made the measurements of the distance to the LMC using Henrietta Leavitt's Cepheid relation. Like Edward Pickering before him, he supported the Harvard computers. Annie Jumpcannon and Antonio Mari were authors on their publications, so was Henrietta Leavitt. In fact, if you cite the Cepheid period luminosity relation, you cite Leavitt. However, he also did refer to the work they did in terms of girl hours. So you win some, you lose some. The final player in this I guess you would say, drama, is a woman named Cecilia Payne, and you will have to bear with me. I'm about to give you a very fast introduction to quantum chemistry. She was from England, and she read physics and astronomy at Cambridge, but she doesn't have a degree from there. Because in 1923, Cambridge did not grant degrees to women. When she asked about what the opportunities were for doing astronomy in England, she was told, you can be an amateur while teaching. Shapley had come, he was now the director of the Harvard Observatory, had come to Cambridge and given a talk, so she knew about the Harvard computers. She cobbled, and as all scientists do to this day, she cobbled together funding and moved over the Atlantic Ocean. Having done an international move with Skype, I cannot even imagine it. When she arrived at Harvard in Cambridge, Massachusetts, because, why mess with a name? She followed instruction. She had followed advice that she had been given to set out to make quantitative the qualitative information that was inherent in the Henry Draper system. So up until this point, they've said the hydrogen lines are stronger in these stars, and they tend to be bluer than these other stars. But there was no numbers associated with it. You couldn't say that an O star had this temperature, because the ability to do that depended on knowledge of a science that at this point was only just getting started, called quantum mechanics. You had to understand the structure of an atom and how electrons moved in that atom. And Cecilia Payne was perfectly positioned to do this. She had been in Europe, so she knew about the Bohr model of the atom. I did warn you we were going to do quantum chemistry. This is a very cartoonish model of an atom. You have the nucleus here with the protons and neutrons and different levels for the electrons, represented here by this lovely blue circle. As electrons move up and down, so if an electron moves down a level, it emits a photon. It emits light, and it emits light at a very specific wavelength. This is actually how you get the lines in a spectra. And there are a series of, and with that very basic model, and if for that electron to jump up to a higher level, it needs to absorb light, and it needs to absorb light at a very, very specific wavelength. So the transitions you saw, the lines of the hydrogen spectrum, are the movements of electrons up and down the levels of the hydrogen atom. And with that knowledge, Saha, here, developed a set of equations using quantum mechanics that could tell you, if you know the atom that you're looking at, which you know from the fingerprints of the spectra, you can determine what the temperature of the gas is. Is everybody with me? Yes. Okay, just checking. I don't normally try to throw quantum chemistry and quantum mechanics at a public talk. Now she did this, so she comes to Harvard, and they happen to have the largest repository of spectra in the world on these glass plates. So she sets about measuring the details of the spectra and applying Saha's equations to determine what the quantitative temperatures of these stars are. This next slide is not to scare you, but to give you a sense of what she did. She did this 20 years before the first computer would be built. And these are the Saha equations. Yes. She did all of this by hand, looking at multiple elements in multiple plates across multiple spectra. And that added the temperature axis of this plot. That tells us that an O star is 30,000 degrees Kelvin. I would say that I would put that into more normal units, but I think when you're up at 30,000, I don't think the temperature scale stops mattering. You know that our sun is about 5,000 or 6,000 Kelvin. And so now we can say that temperature increase, not only just that temperature increases, but exactly what the temperatures of those stars are. This is why O stars had no hydrogen lines. They're so hot that the hydrogen is completely stripped of its electrons. And as you start to cool down just a little bit, you start seeing hydrogen lines again. Now, this alone would have put her into the history books, but she wasn't done. I'd like to remind you, she's still a grad student at this point. For those of you that are having flashbacks to chemistry, I promise I'll get rid of the periodic table in a minute. She could also use those same equations to determine what the universe was made out of. Now, think for a minute. You're living 100 years ago. You look up, and you assume that that is like this. You're going to see a lot of iron, a lot of carbon, a lot of oxygen. There will be hydrogen, and there may be a little bit of helium, but you're not expecting the periodic table, quote unquote, of the universe to look that much different than what you see here on Earth. And so Cecilia Payne looked through the Harvard plates. She did the calculations, again, by hand. And she found that it looks a little different. For everyone that ever hated chemistry, you should have been an astronomer. We have hydrogen, we have helium, and everything else is a metal. But more importantly, hydrogen makes up 75% of the universe. About 25% of the universe is helium. Everything else is a trace element formed in the core of a star. In 1925, this was outrageous. This was insane. This went against all of the prevailing wisdom, and you're a grad student. You're junior, and you're a woman. You're the first woman to ever study for a PhD at Harvard, and one of the first in the world to ever study for a PhD. And Shapley decides, you know what, we need to check with someone more senior who knows about this stuff. This is Henry Norris Russell. He is the R of the HR diagram. And they sent him Cecilia Payne's thesis. And he wrote back to her that it is clearly impossible that hydrogen should be 1,000,000 times more abundant than metals. Note, he hates chemistry. And he convinced her to temper her conclusions in the paper, to say, this is probably wrong. It's a measurement error. Several years later, he published the exact same result and barely cited her. The good news is most of the men in this talk are generally awesome for their time. This guy is a complete, I'm not going to say it publicly. However, Cecilia Payne's thesis, Stellar Atmospheres, a Contribution to the Observational Study of High Temperatures in Reversing Layers of Stars, has been called the most brilliant PhD thesis ever written in astronomy. It would be incredibly impressive work today, let alone 100 years ago. And at this point, the story of the Harvard computers as an active group somewhat ends. This is a transition point. Transitioning from the women being Harvard computers to the women being scientists and considered scientists in and of their own right. The people that I talked about in this talk are only 5 of dozens of women that worked at the Harvard Observatory from 1880 to the 1920s. I'm not even sure a complete list even exists. By the time the Harvard the archive was complete, there were 500,000 glass plates in the collection, each plate containing countless spectra. And they classified and characterized the stars on all of these plates. Annie Jumpcannon, who took over for Wilhelmina Fleming after her death, someone came in and said, I want SW Andromedae. I figure that's in the constellation of Andromeda, but she rattled off the 5-digit plate number, and sure enough, The requested star was on that plate. The work, this is a picture, Cecilia Payne is in the middle, and Annie Jump Cannon is behind her. This work, their work, is the backbone of modern stellar astrophysics. Without these women, we don't have modern stellar astrophysics. Wilhelmina Fleming died in 1911. She was the first of them. She was also one of the oldest. Remember, many of her contributions were cataloging and making sure that the plates were organized, and so that someone could actually find what they were looking for. And even in astronomy, her contributions have been largely forgotten. I actually didn't know her name until I started researching this talk. On her tombstone, under her name and the dates of her birth and death, she simply had written astronomer. And remember, she is the only person that I've highlighted here that did not have a degree in astronomy. Annie Jump Cannon died in 1941. This is a picture of her looking at one of the glass plates. They would mark in pencil next to each of the stars preliminary classifications, possible variables that could then be wiped away afterwards. During her lifetime, she would classify hundreds of thousands of stars. She could look at one of those spectra on the glass plates and say, oh, that's a B2. As casually as you decide as you look at anything. That's a B2, that's a G, that's a M. The OB-AFG-KM spectral classification sequence that she developed was adopted by the International Astronomical Union in 1922, and it is still in use today. And if anyone can come up with a better mnemonic to remember it, I am all ears. She received a prize for her work from a group that supported women in research and in academia of $1,000. And using this money, she endowed a prize in her name, the Annie Jump Cannon Prize. For decades, this was given only once in a while to a deserving woman. It is now given annually to an exemplary early career woman at a United States institution, which I take to mean that there's now more of us than there used to be. Antonio Mari would work intermittently at the Harvard Observatory for decades. One of the reasons this was intermittent is that she couldn't make enough money as a computer to actually live. So she was often doing teaching jobs in addition to her work at the observatory and would burn out, would leave for a while, and would come back. In 1944, she became the second recipient of the Annie Jump Cannon Prize and passed away in 1952. That complex spectral classification sequence, the fact that the spectral lines of some of the different stars looked different, even though their strengths were the same, is now how we differentiate between types of stars. So how many people have seen Betelgeuse, the bloody shoulder of Orion? It's really bright, right? How many of you have heard of Proxima Centauri? Yeah, it's nearest star to the sun. Betelgeuse, but you can't see it from Earth with the naked eye. It is so dim that even at 4.1 light years, it is too faint. For comparison, Alpha Centauri is one of the brightest stars in the southern sky. Proxima Centauri and Betelgeuse are the same spectral class. The difference is in the shape of their lines. Betelgeuse is a giant star, has a much broader line. Proxima Centauri has a much narrower line. And Mari's classification scheme is how we differentiate between those types of stars. In 1934, Cecilia Payne-Gabolchkin received the first Annie Jump Cannon Prize, the only recipient to receive it directly from Annie Jump Cannon. Her prize was $50 and a small handcrafted medallion of a spiral galaxy. She is also other than Wilhelmina Fleming and her short-lived early marriage, she is the only person who I've highlighted here that was married. She went on to become the first female faculty member of the Harvard Astronomy Department. This took until the 1950s. And she became its first female department chair. And then there is Henrietta Leavitt. She died of cancer in 1921. 5 years later, a man you might have heard of, Edwin Hubble, he found Cepheids in Andromeda. And he used that period luminosity relation, that standard candle that Henrietta Leavitt gave astronomy to determine the distance to the Andromeda Nebula, what was then known as the Andromeda Nebula. At that point, there was a massive debate in the field about whether or not objects like Andromeda were internal to our own Milky Way or galaxies external to our Milky Way. Something that we just know now as a fact of the field was under debate. The distance that he derived from the Andromeda Cepheids proved beyond a shadow of a doubt that Andromeda wasn't a nebula. It was an external galaxy that we now know to be 2.5 million light years from our own. Today, the Cepheids form part of what astronomers refer to as the distance ladder. Starting down here with parallax. So if you want an example of parallax, stick one finger out, cover one eye, cover the other eye quickly, and then move your finger in and do it again. Your finger moves. Does your finger move? Yes. When does it move more? Closer. Parallax does the same thing, does the same for stars. But it only works for stars, even today, for stars relatively close to the Earth. We can't even go outside of our immediate neighborhood around the sun, let alone outside of the galaxy. Up here, we have cosmic distance scales, measuring things that are millions or billions of light years away, and we still need to know their distances. And in between are the Cepheids. We use parallax for those nearby Cepheids for which we know parallax. We have their parallaxes. We can get their distance with parallax, and that calibrates Henrietta Leavitt's relation. The Cepheids, in turn, calibrate the even more distant scales. When you hear about the acceleration of the universe, for which a Nobel Prize was awarded, dependent on the period luminosity relation. Whenever you hear an astronomer tell you how far away something is at the edge of the universe, or even only 5 billion light years away, it is dependent on this step in the distance ladder. On the centennial of her discovery of the period luminosity relation, a symposium was held at Harvard. This is something we do in astronomy. We have symposia. And at that symposia, it was recommended that from there on out, the Cepheid period luminosity relation, which is how I learned it and how most astronomers learned it, be referred to as the Leavitt law. The next year, the American Astronomical Society agreed. And while you were asking me questions, I have a little present for you from the 2017 Women of Astronomy. Thank you. Questions?
Yes. Prior to the determination of the standard candle parameter, Cepheid levels, was there a luminosity standard prior to that?
No. Not at this.
You had a chart on earlier that showed luminosity, or as you called it, absolute brightness. Was that somehow different?
She could do it because she knew the initial group that it was done for were all at the same distance. They were all in the LMC. She didn't know the distance to the LMC, but she knew that if one was brighter than the other, it was actually that much brighter than the other. So if you take, so you have this variable of distance. And if something is much closer to you, if you have two things that are the same brightness, and one is closer to you than the other, the closer one will appear brighter. But if those two objects are taken to about the same distance, they will appear to have the same brightness, and they will in fact have the same brightness. If you have one object that's much brighter and is further away, and one object which is fainter and closer, they may appear to be the same brightness, but in actuality, the more distant one is brighter. If you were to take those same two objects and move them to the same distance, the one that is brighter will appear to be brighter than the fainter object. And that was what allowed her to have to build the period luminosity relation, is that she didn't know how far away they actually were, but she knew they were all at the same distance because they were all in the Large Magellanic Cloud. Does that make sense?
Other questions? Over here.
Yeah, I was wondering, was their work instrumental in connecting with Einstein that it was nuclear fusion in the core of stars? You have hydrogen going to helium.
Which her are you referring to?
That's yeah.
It's the question of, was her work instrumental with determining that hydrogen was in the core of stars? And the answer is no. Cecilia Payne's work dealt with the atmospheres of stars, the very upper level, the photosphere that we can actually observe. The physics of what actually happened inside the core of stars was done by other people.
When Evan Hubble was looking for the Cepheid variable in Andromeda to find out whether it was 2.5 million light years away or just part of our galaxy, when you start looking at all these stars with the telescopes they had, how do you know precisely which star you're looking at when you got to do it? That those ladies were doing hundreds of thousands of stars.
You look in the outskirts.
Is it the telescope quality?
The question is, how do you go about looking for Cepheids in Andromeda on photographic plates? And the photographic plates were actually relatively high resolution. You could see a lot of individual stars on those plates, especially in galaxies as close to us as Andromeda is. You would then take an extremely powerful magnifying glass, and what looked like a cloud of stars would actually resolve out into individual points of light. You also would not point the telescope at the very center of Andromeda. You would look sort of slightly out from the center where the stars weren't quite as dense, and it is still a technique that astronomers use to this day.
All right, all in the back there.
In your beautiful image, there are a lot of blue stars for a very old cluster. You explained that the HR diagram is an evolutionary diagram. Can you explain the blue stars?
The blue stars are what are called horizontal branch stars. So some stars evolve off the HR diagram. They evolve into the giant phase, and then they go through sort of an oscillation, where they go from the red part of the diagram over towards the blue and then back. And they're not, when they move back towards the blue, they're not burning hydrogen, they're actually burning helium and then eventually carbon and oxygen for the most massive stars. And every time they have to burn another element, so when they evolve up to the red giant, they get hot enough to burn helium, they move over. And then when they run out of helium, they go back, and they just move back and forth until they run out of fuel to burn, at which point for those stars, they're going to explode in a supernova.
I would also note, in the image that we gave out today, the blue here actually represents ultraviolet light. This image was taken with ultraviolet, visible, and infrared detectors on wide field camera 3, so the colors are stretched beyond the visible light in this image. Okay.
Visually, Omega Cen looks yellowish when you actually look at it.
If you look on back, on that, you get that?
Yeah.
Yeah, you get it as on the yellowish view of Omega Centauri. All right.
Just as a curiosity, Omega Centauri can be seen from Baltimore.
No.
It showed up in one of my Halley's Comet pictures. It's about 3 degrees above the horizon.
Yeah, if you're very lucky in Baltimore, yes, you can see it.
You're way down against the horizon, aren't you? There, so that's tough.
In astronomy, you do not observe a megacent from the northern hemisphere. The telescope operator would kick you out of the room.
Yes.
If you could name a space telescope after one of these women, who would it be and why?
So the question is, if you could name a space telescope after one of these women, which one? You have a space telescope, we have a Canon space telescope, we have a Payne-Gaposchkin space telescope.
It would be one of those three. I think it would depend on what the mission of that telescope was. If it was a telescope to push the distance ladder, then you name it for Henrietta Leavitt. If it's a telescope whose primary mission is going to be to go after stars, Annie Jump Cannon. If you're probing fundamental physics, Payne. So I think it would depend, but I think it's high time we named a telescope after one of these people.
I can second that. Other questions we have? Down here. Yeah.
Could you review for me, please, the absorption lines? Each element has its own absorption pattern, or are we referring to something else when we're talking about absorption pattern?
Each element has its own absorption pattern. We usually talk about them the way that you think about fingerprints. The specific sort of swirls within your finger may be repeated in another person, but the combination of those patterns on all 10 of your fingers is unique to you. And the same thing's true of the different elements. There may be a line very close to hydrogen alpha for another element, but the pattern of hydrogen alpha, hydrogen beta, and hydrogen gamma, and hydrogen delta is unique to hydrogen. And you look for those patterns rather than the individual ones.
All right, any last questions? All right, I see that Irini is here. So everyone say hi to Irini. She is our telescope operator for the Maryland Space Grant Observatory. And if you would like to go look through the telescope, she will take you. Are you going to come down here? So that because people are going to be leaving from over there. So if you would like to go across the street and meet with Irini, and she'll take you across the street. Next month is to be announced, but I will have a speaker for you on June 6th. And let us give a very warm thank you to Mia Boville. Well, the point was that, you know.
The point was this was hard. This is a pain in the ass. This is a pain in the ass.
I've shown the Christoffel symbols. Yes. Okay. Let me try this again. There we go. Okay, there we go. Now we got it. We're back. Great. But you know what? Sometimes we just get it right. So this is our picture of Jupiter at opposition from this year. Isn't that cool? I mean, I remember when we had to have the Voyager missions to go across interplanetary space to get something that looked this gorgeous. And I just love all of the hydrodynamic effects, okay? I'm a sucker for all the hydrodynamic effects of the vortices and the swirls in Jupiter's atmosphere. Plus, you'll notice we've got not only the great red spot, But also we have what we colloquially call red spot junior, officially called oval BA. I much prefer red spot junior. And oval BA formed in the year 2000, okay? We had never seen a second red spot until it actually, well, it formed as a white spot and then turned red a few years later. But it has now been around for almost 15, 20 years. Okay, so we're seeing a second red spot on Jupiter, and it appears to be, all right. So every once a year, Jupiter gets into what's called opposition, okay, where the Sun and Jupiter are on the opposite sides of Earth. Well, this is the point in Jupiter's orbit when it is closest to Earth, because you can see that if it were located anywhere else around its circle, around its orbital circle, it would be further from Earth. So the best viewing, its closest point, is at opposition. Also, it's its best viewing because it's up exactly opposite the sun, so it's not up at sunset, not up at sunrise, where you have interference of that, and you can see it. Now, Hubble doesn't have to worry about that too much, because Hubble Hubble's up in space, and it doesn't have to worry about, you know, daytime versus nighttime, because, you know, it doesn't have the atmosphere to look through. However, we often take pictures of the planets when they are at opposition, and you might think to yourself, well, we've had missions that go to the planets. What can Hubble offer? And I sometimes look at these press releases we do and go, okay, but you know what? Whoops. Well, let me replug. You know what? This is an observation we have yet to take. In August, I have a really cool talk for you. The View from Mission Operations, that's not the title. I just made that up this afternoon. She hasn't given me a title, but Courtney McManus, who has worked on mission operations for the International Space Station, and we have the missions operations here for JWST here in the building, so we'll be telling you all sorts of cool stuff from a mission operations standpoint. August 1st, 2017. Can't remember all that? You can go to our website on Hubble site. And by the way, Hubble site has been, design has been changing. I don't know how many of you go to our Hubble site website, but we've been changing it and modernizing it. All the content is still there, okay? You can still find us. Finding this page is probably the easiest. If you go to your favorite search engine, type in Hubble Public Talks, you'll find this web page. On the web page, we have our links to our live webcasting, links to the archive all the way back to 2005 in the STSCI webcasting archives, as well as a way to sign up for our email list to get our couple reminders a month about the talks that are coming. The announcements, again, sign up at the website, but if you want to do it the hard way, you can go to maillist.stsci.edu. The mail list is called Public Lecture Announce. If you would like to ask us questions, send us comments, you can send email to publiclecture@stsci.edu. For those of you who like social media, Hubble has several ways of communicating: Facebook, Twitter feeds, Google+, and Pinterest out there for those of you who use those social media. Myself, I have a blog on Hubble site. I have Facebook, Google+, and Twitter that I occasionally do. But unlike the president, I have better things to do with my time. So I have a tendency to do my science rather than spend too much time on Twitter. Okay. Observatory tonight. Yes, the weather is permitting. I talked with Irini, and she should be here about 9 o'clock or so to take a group across the street to look through the telescope across the street. So at the end of the lecture, if I forget, somebody remind me. You'll meet down here with Irini, and she'll take you across the street. All right? And now, okay, my section. News from the universe for May 2017. Our first story tonight, by Jupiter. It's quite a beautiful planet. Thomas, can we take the lights down a bit? There's a little a bit of spillage onto the screen here. Okay, that's good. Thank you. All them. We have our beautiful, beautiful pictures tonight. Special request by our speaker that you have the core of the globular cluster Omega Centauri. Okay, and all these beautiful red and blue stars, which are actually ultraviolet and infrared as well as visible light. It covers the full spectrum with wide field camera 3. It's beautiful. More details available on the back. And I hope our speaker will actually talk about that a little bit tonight. Who is our speaker? Our speaker is Mia Bovel. She is going to talk to you about the Harvard computers and the classification of stars. Of course, this was work done a century ago, so computers is in quotes, and you'll understand that in a bit. Next month, I've been having trouble getting people to commit to June. Usually July is my problem, okay? But I've had people trouble, so it's still to be announced, but I'm working on it. Trust me, I'm working on it. I'll find somebody's arm to twist for next June, June 6th. July has actually been moved early because we have Amber Strawn from Goddard Space Flight Center here, and she will be talking on dark energy and new worlds, the science that is we hope to accomplish with NASA's W1 mission that will hopefully launch sometime next decade. There will be no lecture in July because we're taking Amber's lecture and counting that as our July lecture.